Look at how most enterprise software integrates artificial intelligence today. The AI operates outside the actual flow of human collaboration. This diagram maps the standard network topology of a modern meeting. The human participants connect to a central conferencing server, while a separate AI node sits isolated on the perimeter, passively receiving a flat stream of text transcripts. Because it sits on the outside, it can only react after the fact. It cannot participate synchronously while the work is actually happening. Bolting an LLM onto a legacy video conferencing tool creates a latency gap. You get retroactive summaries, but you lose the ability to perform live, concurrent teamwork. Parivox takes a different approach. It is a developer platform that treats the mixed human-AI environment as a programmable primitive. Instead of keeping the AI on the perimeter, Parivox moves the agent directly inside the WebRTC infrastructure.
WebRTC enables real-time peer-to-peer communication in web browsers. Here, the AI becomes a first-class participant. It can simultaneously listen, speak, execute tools, and drive the interface. This structure provides a new operational foundation for developers building on the LiveKit framework. LiveKit is an open-source real-time infrastructure platform built on top of WebRTC. Achieving actual AI integration requires re-engineering the virtual room from the ground up, rather than adding a conversational chatbot to a sidebar. To make an agent a live participant, the system relies on a sub-500 millisecond processing loop. This secular flowchart details the agent pipeline. The first phase is perception, where multimodal signals, including STT, room state, and chat messages, flow into the processing core. STT stands for speech-to-text, a low-latency transcription process that converts spoken audio into machine-readable data. Next is reasoning. An LLM evaluates these incoming streams to decide on an immediate course of action. An LLM, or large language model, is an AI system trained on vast amounts of text to understand and generate human language. Finally, we reach the action phase. The output splits into two outbound paths: audio generation via a TTS module and structured data payloads. TTS, or text-to-speech, is the synthesis technology that turns text outputs back into human-like audio. Instead of forcing one monolithic model to handle everything, Parivox routes these distinct phases to specialized API providers, like DeepGram for transcription and ElevenLabs for voice. By keeping this pipeline continuous and modular, the system transforms a delayed responder into a synchronized, low-latency room member. Bringing multiple speaking agents into an unmanaged audio environment immediately creates collisions. Parivox solves this through a system-level policy layer called the Room Etiquette Contract. This logic tree demonstrates floor token governance. To broadcast audio, a node must possess a single shared token. If an AI node attempts to speak without it, the system blocks the output. The system also enforces an instant yield logic. If an agent is speaking and a human interrupts, the system immediately revokes the agent's token and severs its audio output. Agents also process effective backchannels, like laughter or a hesitant allowing them to adjust their conversational timing without losing the floor. Strict conversational arbitration ensures a room with multiple humans and AI agents remains usable and coherent. Parivox agents operate across both audio and visual layers simultaneously.
They generate structured visual updates synchronously during an active conversation. This data flow visualization maps how that works. Parallel to the primary audio stream is a secondary data channel. It utilizes LiveKit RPC and data channels to bypass standard text output and drive the interface directly. RPC, or Remote Procedure Call, is a protocol that allows a program to trigger actions in a separate software layer. Through these channels, agents can generate and manipulate live artifacts, reordering agendas or updating charts as the humans talk. The system links these visual updates directly to time-stamped transcript events, ensuring every action has an auditable record. Visual co-presence bridges the gap between passive transcription and active operational work. The AI alters what humans see on screen in real time. Engineers configure these mixed environments using the Parivox Studio environment. They use room and agent templates to define operational roles, set behavioral policies, and grant specific access rights. To connect these rooms to external software, Parivox uses the OpenClaw gateway. This node map illustrates the architecture. The Parivox room securely gates the OpenClaw gateway, which translates conversational commands into secure API pushes to external databases and business systems. This execution layer is sandboxed and policy-gated, preventing the agent from making rogue or unprompted changes to an external platform. Empowering an agent to execute external tasks turns a basic communication environment into a legitimate operational workflow engine. Developers are not restricted to hosting these rooms inside the native Parivox workspace application. Look at this split-screen layout. Developers can package a fully configured room and its agents into a clean HTML embed snippet. This allows external users to instantly enter live, agent-guided sessions directly from a website without creating an account. Companies deploy these snippets to create embedded sales engineers on pricing pages, guided intake flows for medical portals, or interactive product demos. Distributing the underlying WebRTC room architecture anywhere on the web multiplies its utility for software teams. Standard meetings suffer from a temporal limitation. When the session terminates, the contextual data vanishes. Parivox solves this with persistent room continuity. This timeline depicts the end of a meeting. The room's transcripts, decisions, and artifacts collapse into a distinct vector block and slot into an ongoing PG vector database. This Postgres extension stores and queries high-dimensional vector envenens, making semantic search possible. This persistence layer transforms an ephemeral audio stream into a stateful, queryable data structure. When participants re-enter a room, the AI instantly pulls that previous vector block to populate the new context layer and brief the team. Persistent memory converts a one-off taskbot into an ongoing digital collaborator. The complete Parivox stack combines real-time audio, token governance, UI manipulation, and persistent memory. This structure replaces the isolated post-processing AI models that currently dominate enterprise communication. It solves the integration problem by treating the room, the agents, and the generated artifacts as a single programmable unit. Here, we see the final architectural result of this integration. It fundamentally shifts how software engineers can approach user interaction. The stateful AI-native room has become the primary unit of enterprise software.